Okay. We'll talk about the static equilibrium of the rigid body. And so, first things first, what is a rigid body? So let's take a body, anybody, and well, you'd say that is not rigid. It looks like squishy, like a jello, but that's just the shape. What makes it a rigid body is that between any 2 points, let's say I and J, we have a vector line, a fixed distance. And that distance, the magnitude of this vector V is constant. Well, and so you can turn it, translate it, you can do whatever. It won't won't change. What is then a not rigid body? Say a not rigid. That is a it's called a spring. And a spring, for example, if you pull it down, it begins like, let's say we have 2 points here, and then this point is actually gonna be like down here. So the V has changed. So that is not original. Okay. There we go. That's a rigid body. And so now we have equilibrium. And so we know that in equilibrium, all the forces external are equal to zero and all the torque equal to zero. And so let's get a a a bridge, let's say. So here we have the land. We have water over here. We have our bridge. And how's our bridge? Our bridge is something like uh, something like this. Okay. Actually, no, bridges are meant to be upright. So here's our bridge. It's got holding here. Oh boy, how's this supposed to work? Like something like this. Okay. That's holding on to it. Maybe we can have something like this. Yep. This is holding. And so by its own, it has a weight, and that weight is pulling down. Okay. And that weight is being sustained by here. We're applying a force here. And that is applying a force back here, which is a force implying a force here, and the ground is employing a force back. Okay. Same thing on the other side, and here it's divided into, okay, it's divided in 4. So if a person stands here, it's going to apply more force. And we can see that the bridge not moved. So it's an equilibrium because all the forces sum up to 0. Also, when um, when a for example, motorcycle is going is at 0 kilometers per hour or at 100, it's considered stop because if the velocity is constant, speed is constant, it's the same thing as acceleration equals to 0. Doesn't matter the speed, the velocity. Okay. Uh, okay. Uh, so now let's do an example, real life example. So we got a two two balances over here. Okay. Okay. So we've got uh two two waste. Got two scales, and we got a rod, like something between the two. Okay, there we go. And so here we have a force going down. Let's say this rod is 10 kilos, right? So should be here 5 and 5 over here, right? Because if you sum these two up, you should give 10. That gives 10, okay. But in this case, it's way less, okay. And so we have a something that's upon. And if it were like right in the middle, we have a mass, right? And so here it would be saying half of the mass, and here half of the mass, okay? And so with that, we know, so now it says that here we have 3 meters. The whole thing is 3 meters. And we have the boxes right here. And this over here. This is not the scale, and this is 0.5 meters, okay? And I want to know what's written here, what's written here. Okay. And we know the mass of the box. So we know that the force that is written on the left less the force that is written on the right, well, that must be equal to the mass. And we're given that the mass is 60, actually the weight, not the mass, is 60 newton. 60 newton. So the force of the left plus the force of right minus 60 newton, well, that's equal to 0. And well, I know that uh, the torque are equal, like all torques, the sum of all torques uh, is equal to 0, right? And that they are equal. That implies that they are equal. So the torque of the right is equal to the torque of the left. So the torque of the right minus the torque of the left, well, that's equal to 0. And torque That's F times R. And so, well, the F of right, so it's F right times R, which on the right we have 2.5 meters, plus F of the left, point other way around. Okay, 2.5 left, okay, plus 0.5 right. Well, that's equal to 0. So, this is a mine. And so 2.5 FL, well, that's 0.5 FR. And if we divide by 0.5, what we get is that FR is equal to 0.5, to 2.5 divided by 0.5, which is 5 FL, okay? So we had FR plus FL, which is 6, no, is 5 FR, that's equal to 0, 6 newtons, right? And so now what we get is that 6 FR, that's 60 newtons. So F of R, well, that's 10 newtons. And I just made a mistake because I'm changing F of R and F of L. So actually F of R is F of L. So here we got 10 newtons. This is F of L, okay? F of L. That's left. Okay, and so F of R, etc., 10 plus 50. And so now I want to make like a general equation, okay? So what do we need? We need the mass. So we need the mass of the box, okay? So my equation needs to have mass. Oh boy, this ain't working again. Mass of box. We need L, which is total length. And I don't know if that's how you write it. We need like we have L total, like L to the, oh, L is the total length. No, okay, so we need L to the left, so L right to the right of the box and L to the left of the box. Okay, so it would be the force, sum of forces, F of R plus F of L must be equal to the mass. And we just figured out that also that the torque of the right plus the torque of left, that must be equal to 0. And we know that torque is F of R times the radius, which is LR times, okay, so that's FR times LR plus FL times LL, that must be equal to 0. So FR LR is equal to minus FL LL. Oh, okay. Okay, so how do we do this? We can say that f of r plus f of l, that's minus 60. That's equal to f of r, l of r, so that would cancel. No. Okay. So we have these two equations, and with that we can like solve it. Okay. That's what we need to know. And then we just plug in the number and we can find, okay, so FR, LR, and I would find F of R. So F of R, for example, F of R plus F of, actually, F of R is what? FL, L, L, oh boy, F of L, 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 over LR, here's negative. Okay, and so before it comes a FL minus FL times LL over LR, that's equal to mass. And then we would find F of L, and then F of R is equal to mass minus F of L. Yep, so you just need these two equations. Let's try that. F of L, the force in the left. Oh, that's what we're trying to know. Yep, didn't know. Force to the left. Right. So F of R, how did I do it? Up here. Yeah, so we need to use this, but I think